Tonight, I'm pleased to welcome you to the second to last talk in this series. And the last one is going to be in 2 weeks. I'll say another word about that in just a moment. I'm welcoming you this evening on behalf of my co-coordinators for this lecture series, Professor Stephen Daunt from the Graduate School of Oceanography, Professor Art Spivak from the Graduate School of Oceanography, and Professor Judith Swift from Communication Studies and also Director of the Coastal Institute. I'd like to thank our major sponsors for this event and this entire lecture series, the J. Unger Vetlesen Foundation, which has been supporting the Graduate School of Oceanography for many years, the Graduate School of Oceanography, which is celebrating its 50th anniversary this year, and there will be a series of events over the course of the next year and culminating really in June that will celebrate this anniversary, and we hope you'll keep your eyes open for those. And the co-sponsors for this program are the URI Coastal Institute and the URI Honors Program. Our special sponsors this year have provided some additional support for specific lectures, and I'd just like to recognize them quickly. The URI College of Arts and Sciences, the URI Harrington School of Communication and Media, a new program, and Rhode Island Sea Grant, which is celebrating its 40th anniversary this year also. I'd also like to note that you can find a lot more information about this lecture series, including detailed bios about our speakers and some additional recommended reading, as well as the archived videos from past speakers at the website for this series, which is www.uri.edu/Vetlesen. So I also just wanted to note, as I mentioned before, that our last lecture in this series will be taking place in 2 weeks, right here, on April 26th, and that will be Senator Sheldon Whitehouse, who will be speaking about the national ocean policy that has been recently enacted and details about how that program will actually be implemented. I also wanted to let you know that on that very last talk of the series, there will be a special reception ahead of the program at 6:30 p.m. in the Edwards Auditorium atrium with coffee and cookies. And this will be an opportunity for the honors students who have been taking a class associated with this lecture series to present posters about all of the information that they have gained over the course of this series. So we hope that you'll join us for that, 6:30 on April 26th. And finally, I would like to welcome Dr. Tatiana Reinierson to introduce our speaker this evening. Dr. Reinierson is a professor at the Graduate School of Oceanography also, where her research focuses on the ecology and evolution of plankton using genetic techniques. Dr. Reinierson works with me as co-director of the Metcalf Institute, science co-director, I should say, of the Metcalf Institute. And she's also director of the long-term plankton monitoring survey at the Graduate School of Oceanography, which is the longest plankton monitoring survey in the world. She is co-director also of the Center for Excellence for Marine Life Sciences, which is a URI EPSCoR funded program on the Bay campus. And then finally, before I welcome Dr. Reinierson to the stage, I just wanted to remind everyone to turn off their cell phones if you have not already done so. Open your candy wrappers, get all of your crinkly paper out of the way, and enjoy the lecture.
All right, thanks everyone. So it is my pleasure to introduce you to Dr. Deborah Kelley from the School of Oceanography at the University of Washington. She's a professor of oceanography and she researches deep sea hydrothermal vent systems. And as you're going to learn tonight, her contributions to oceanography and marine science go far beyond the specific focus of her research. Professor Kelley has had an enviable career and has made spectacular discoveries that have changed how we view the ocean. She has worked on some of the most extreme and fascinating ecosystems on the planet and explored the link between submarine volcanism and the conditions that support a surprising diversity of life in the deep ocean. While on a research cruise in the Atlantic Ocean, she discovered a new type of deep sea vent on the mid-Atlantic ridge. She named this the Lost City Vent Field. It is driven by a different mechanism than all the deep sea vents that had been previously discovered. Her discovery of the Lost City was then outside the box of processes that we thought occurred in the deep sea, and it also shed new light on the diversity of life on this planet. And it also helps us understand how and where life exists on our planet. She's also done an amazing job of bringing oceanography to the public. She's worked with NOAA's Office of Ocean Exploration to develop new outreach programs, and she's brought many high school teachers, undergraduates, and graduate students out to sea with her. Recognizing the value of technology to oceanography, Professor Kelley has served as the head of a science steering committee which oversees the use of our nation's scientific deep vehicle fleet. So she's really played a role here in helping to shape the kind of science that we're doing in the deep ocean. So as you're going to hear tonight, Professor Kelley is also working hard with a team of engineers and scientists to bring a new level of monitoring and connectivity to the oceans through the use of undersea observations that are connected to land via fiber optic cables, transferring data to us about the deep sea in real time. So finally, I do want to highlight Professor Kelley's educational background, which includes undergraduate and master's degrees from the University of Washington and a PhD in geological sciences from Dalhousie University in Nova Scotia. Her career in oceanography really started with her first marine science class in her junior year in college. She is a self-labeled scientific late bloomer, and to the undergraduates in attendance this evening, she's a great example of what you can achieve once you find your passion and you run with it. Here's Dr. Kelley.
Thank you, Tanya. So while I was sitting there looking at this slide, I recognized that I have an extra 10 additional years to do science, and it's not really, so it's definitely my pleasure to be here, and I've been treated really well. So I'm anxious to share kind of a definitely new thing that's going on in oceanography, and I spend a lot of time working on this now, and part of the reason is I have a lot of passion for it, and I think that it's a program that will forever transform how we look at the oceans, the ability to interact with the oceans, and a global population of people that may not have access to the oceans will have access through this program. So I'll share with you some of the background. I'll focus a little bit on there's some major components to it, and then I'll dive into the fiber optic cable and why I think it's so profound. So I definitely, not growing up in an academic family, I spent a lot of time thinking about what I was doing, and I feel gifted and have had a very special life, I think, by finding a niche that I'm passionate about. I love going to sea. I love interacting with people. Most oceanographers have interesting personalities. And life isn't boring, and I really am passionate about taking students to sea and showing the ocean and giving them real hands-on experience. But not everybody can do that, and so one of the, I think, unique opportunities for this program that we're in the process of installing is that it really will give access to people that can't go on boats necessarily or see the ocean. So one of the things I want to drive home is the oceans are, as you know, living on the oceans, it may be obvious to you, but a lot of people don't recognize the planetary importance that the oceans drive. They drive most of the processes on the planet, and they're critical to the quality of life on Earth. They really are the last unexplored frontier on the planet. We probably have mapped 1% of the oceans with the kind of resolution that we need to do a lot of the kinds of studies that I do. Latitude was a great example. It was never hypothesized. We stumbled on it, and it really changed. It's actually changed models for the origin of life on the planet. So we have these. I think in the next few decades, there's going to be really profound discoveries made in the ocean still. The oceans drive the atmosphere, they drive climate, and there's also a growing urgency to understand the oceans. And I'll spend a little bit of time on that in a minute. But so everyone knows it covers 70% of the surface of the planet. But what people may not recognize is that over 70% of the volcanism on the planet also occurs underwater. And we've been going to sea for a long time, but we've only actually, in the last 5 years or so, actually witnessed underwater eruptions, and there's some really amazing things that happens during those eruptions. I'll talk about that in a little bit. There's a source of hazards. We all certainly came home to life over the last couple of years looking at the underwater earthquakes and tsunamis. And as I mentioned, the ocean is a planetary flywheel for the climate. So when we recognize that, we have a profound influence on our oceans right now, and societally, we're impacting the oceans more and more. So with that recognition in mind, and recognizing that, traditionally we've gone out on ships for a month, 2 months, and maybe for the work I do, if I'm lucky, I get to go back to the same hydromet field maybe once a year. I work in the Northeast Pacific, so our weather window is 3 months out of the whole year, and it just turns out that during big storms, usually in the winter when there's been an underwater eruption, that's when it occurs in the winter and you can't get out there. So these major events that actually put a lot of heat and chemical energy into the ocean change the kind of biodiversity there. Often we're not in the right place at the right time. And so this project that we're working on is to have an awareness about a growing awareness of the oceans for the large portions of the population, but also to be there in the right time at the right place. And eventually, as pressures increase, we really need to be able to predict how we influence the oceans, and how the oceans influence the climate. And people think it's not possible to manage the ocean, but we certainly do that now. We just don't do it in a very knowledgeable fashion. So one of the main take-home points is, I think whether people know it or not, people that live on the continents, the oceans impact us. They impact crop production. So we really need to have a better awareness and understand why the oceans are critical to the habitability of the planet. So I don't know if you've seen this before, but what it's doing, it's going to play over time. It's a few years old now, but what we're showing is the temperature of the oceans. It's just one single parameter. And you're looking at temperature anomalies, so just a couple degrees, with the warm being warm when the water's a little bit warmer, and the cools when it's colder. And so if you look at, in this case, the Pacific, and even put your eyes over, so the other thing to notice is this green is when there's crop die-off and when there's vegetation increase. So if you take a look at, say, the Pacific, and you look at the dance of the ocean temperature here, and then you turn into the Horn of Africa, and you watch the greens change over time, what you start recognizing is that the temperature changes, just one single parameter in the Pacific actually fundamentally change our food production, vegetation, a lot of it's food production, on other continents. And so if we can start understanding why these changes happen and be able to better predict when they occur, we may be able to have better guides for when we can look at areas that might undergo crop failure. So it's very critical, and I think the more and more as I work in this field, I recognize that there's a growing urgency, and this is kind of a dynamic or disturbing image, but if you recognize that right now there's about 1.2 billion people that are on the edge of starvation, and the population is definitely increasing, there is an incredible urgency. For the students in the audience, when you're my age, there's going to be another 2 billion people on the planet, and so we're already recognizing a trade-off between, if you look at other countries with water, even in this country, water is going to be a big deal, how we manage the planet, how we develop crops, how we deal with a lot of the pressures that are only going to increase. When you take that back to the ocean and recognize that it really does govern the weather, food production on a lot of parts of the planet, you recognize that we really need to have a better understanding of the processes that go on. So other things that are happening on the planet, you've had talks on climate change. So it took about 200 million years or so for the carbon reservoir to form that we're burning and have burned up in the last, say, 200 years. This is an old slide now, but what you recognize, and everyone is pretty current knowledge right now, is that a lot of this CO2 is building up in the atmosphere, and it's a very nonlinear process. And this is just a record from Mauna Loa. So the ocean's critical because over half of all the CO2 that's emitted into the atmosphere goes back into the ocean. So it has a great feedback loop that is both profitable or beneficial to the planet, but it also means that we are fundamentally changing certain properties of the ocean. So I showed you just a few parameters and some things that I think are really important, some take-home messages. As an oceanographer, one of the things I love about it is it's incredibly interdisciplinary, and I wouldn't have known that when I was first starting out as a geologist. And so if you look at this, you recognize there's a lot of different processes, and as an oceanographer, I might study, my love is underwater volcanoes, and I know them quite well, but there's a lot of complexity in the ocean. And so to get at that complexity and start having more eyes to the ocean and more different kinds of scientists that look at that, the National Science Foundation got a large grant from, it's a line item, it's a $385 million grant for the Ocean Observatories Initiative. And this kind of award is usually a one-time deal, and it's traditionally it's been saved for atmospheric or planetary observatories. So things that will fundamentally change how you do your science. And for us in oceanography, where we've been limited by ships, we'll always still do expeditionary science. We'll always go out in ships. But we don't have long-term time series at the right scales of observations from, millimeters, sub-millimeters to ocean scale processes and over very long time scales, because we just aren't often in the right time at the right place. And we may have a few places throughout the ocean, but we don't have very many of them. So the Ocean Observatories Initiative is an effort to have a telepresence, a sustained presence in the ocean in places that are critical to starting to understand some of the major processes that go on in the ocean. There's some major components. Let me see if I can get back here. So there's global moorings down in the off of Chile and off the Argentine basin. Very, very dynamic areas, very high winds, high seas, and I'll show you some information about CO2 and why these areas are so critical. There's another set of global moorings that are up in the, so we're looking at the high latitudes now, up off Greenland and in the Gulf of Alaska. And these moorings are specifically set at these key sites. They'll be putting data onto satellites, and then the data will come back to shore over the internet. And so there'll be some real-time components. But they don't have quite the high power and the bandwidth that these cable observatories will have. To look at coastal processes, things like western boundary currents and eastern boundary currents, near shore environments, there's a lot of fundamental changes that are going on there. There's two arrays. One is the Pioneer Array, which is an array of moorings and gliders that will be moved around every 5 years. And then off the Pacific Northwest, off of Washington and Oregon, will be the cabled observatory and another smaller observatory of uncabled moorings. And so what I'm working on right now, I spent the last 3 years pretty much full time working on cable observatory. So I'll show you a few examples of why the global moorings are so critical, and then I'll zoom in and talk a little bit about the cabled project. So again, I mentioned that the Ocean Observatories Initiative, it's a $385 million project. It's a very large project for oceanography. It's not at the NASA scale, but for us, it's quite large. It's going to take about 5.5 years to build. We're in the second year. And with operations and maintenance, it turns into about a $700 million project. So this, it's a lot of money for oceanography, and we went through very strenuous reviews, a long planning process. We had meetings with over 300 scientists, and they helped guide the key locations of where these instruments are going to be. But again, the vision is to launch an era of scientific discovery across and within the ocean basins using widely accessible, scalable, interactive telepresence. So we can not only interact with the sensors and change how they're behaving, how many samples they're taking over time, but we also bring the data live. And that integration is being looked after a very large cyber infrastructure component that's led by UCSD San Diego. The global part is led by Woods Hole. They're looking at the large mooring arrays that will be out there, and they also partnered with Scripps and Oregon State University. These were competed proposals, so groups got together and competed for them. The Cabled Observatory, which I'm involved in at the University of Washington, is led by John Delaney there. So there's I think some pretty fundamental differences, and it used to be, it still is for a large part of research, is that because your data was so valuable and you spent so much time trying to get funding for it and collecting it, that a lot of your 10-year process was, this is my data, and I'm going to hold on to it. One of the major changes with this observatory is all the data is open access. So as soon as it comes in, it goes through a quality control process, but it's open access for everybody. And it'll be on the internet, so anybody can look at it. And it includes, there's several thousand sensors that'll be on this network when installed. It'll be real-time data. It'll include things like high-definition imagery, mass spectrometers on the seafloor. It's interactive. We're looking at processes that go on from microseconds to years. And we're looking at everything from how microbes evolve in submarine hydrothermal systems to how large currents impact, say, the Pacific Northwest. NSF, because they've believed in the project so much, they've committed 25 years of operations and maintenance. So our designs are largely driven in part to make sure that what we put in the water will be sustainable over time. And again, it will be accessible to everybody over the internet. So for the global moorings, there's 4 sites, again, Station Papa in Alaska, one off the Urmaging Sea, southern Chile, and Argentine Basin. And this is a set of 3 moorings over 50 kilometers areas, and then they'll have gliders to give you a 3-dimensional array, and several different kinds of sensors that look at the chemistry of the oceans, some of the biological properties. And why is that so important? Well, if you remember when I mentioned that over half the CO2 from the atmosphere is pumped back into the ocean, one of the drivers for that is if you look in these purple, these purple areas up in here, and this is where the moorings are, you'll see that this is where the really, really high winds are. So it's a place where in 80-knot winds, you don't often get too much work done, but these moorings are designed to, there's some that are surface piercing and some that are below the big wave action. So we're looking at very dynamic processes year-round in this environment. And again, that directly is related to the CO2 that's pumped back into the ocean. When there's large waves, it takes the bubbles that form in the large waves capture the CO2, and they bring it back and dissolve back into the ocean. And so you can see up above Greenland, in this high latitudes is where a lot of the CO2 is pumped back in the ocean. So we have, in addition to this, we have long-term models that have these predictive capabilities, but often we don't have a long enough time series of data or in the right place at the right time to really predict in 50 years what the ocean is going to look like. And when you start thinking of climate change issues, this is a really fundamental type of measurement that we have to make. And this just shows you again some of the CO2 here. Again, at the high latitudes where there's a large flux of CO2 into the oceans. So the high latitude observing systems, this is an example of the Urmaging Sea, very high winds, large waves, a lot of energy exchange between the air and gases within the atmosphere. It's a major area for high productivity in the ocean, important fisheries, and again, it's very, very sensitive to climate change, and a lot of the biological communities in these systems are responding to events that can be induced by us without a lot of knowledge of what we're really doing to the planet. So that's a quick introduction. I could talk more about it if you have questions later on about the global portions of the network. It turns out that the Northeast Pacific wasn't totally planned this way, but it's the most densely populated area in the world right now for cabled systems. And it's also a great place because it's the one area on the planet where we have Global Station Papa, which is part of the Ocean Observatory Initiative. And then this is about the footprint of the cabled observatory here. So this is Vancouver Island. But we also have another cabled observatory off of California called Mars. And then the Canadians, we partnered with them early on. And they were able to install an 800-kilometer system on the northern part of the Juan de Fuca Plate where we're working, and I'll show you some of that. So it's one place where within the next 5 years, we're going to have a large amount of infrastructure to look at large-scale processes in this environment. It turns out that this is a very, very productive area. It's one of the major, for certain kinds of fish, it's one of the major breeding grounds for fish. And the reason that this was chosen here is to look at some very large-scale processes and how the chemical changes that are taking place. This is a very strong area for ocean acidification. I'll show you a slide in a second. How these processes from seconds to decades change and impact each other. So how does the biology affect the chemistry? How does the chemistry affect the biology? Things like that. So this is what the Cable Observatory looks like. This is the Neptune Canada system. They were awarded, the Canadian Foundation for Innovation had a one-time award. And we had partnered with them early on, and there was a memorandum of understanding that they would put in the northern part of this Cable Observatory on the tip of Vancouver Island here. This is the Juan de Fuca Ridge Spreading Center. It's a very active hydrothermal site as well as a very volcanically active site. There's a large fracture zone right here. And then this is the infrastructure that we're putting in, we're just starting putting in now. So there's a shore station off of Pacific City. This is the shelf and break slope down into the abyssal plain. This is about a 400 and some kilometer fiber optic cable out to the spreading center. And I'll talk about some of the processes and why, some of the science that we're interested in working on here. From there it goes, there's another site that couples to some of the coastal studies. These are cabled moorings up here, and then there's a site off of Grays Harbor, Washington, that are uncabled here. From there it goes over two backhaul systems. There's a large internet fiber optic system that runs north-south. We'll transport some of the data up to Seattle, where the operations center will be for the cabled. You can imagine managing power over 400 or 500 kilometers with nodes on the seafloor is an interesting engineering endeavor. So we'll have an operations network here, and the data goes off to the internet down to UC San Diego, where it gets transported. It's pretty much almost instantaneous. So it's a very large, I didn't know anything about engineering when I started this project. We now have about 33 engineers, so I've learned some interesting language and jargon, and they're fabulous people to work with. So the cabled observatories, you may not know it, but most of your phone calls now don't go over the satellite system. Most of them are all carried by fiber optic cables, either on the terrestrial grid or underwater. And it turns out that the coast of Oregon is where most of the submarine cables come on shore for the west coast of the United States. So we early on hired a person that was vice president of Tyco, which is one of the major industry cable laying companies. And his name is Pete Barletto. He's brought a lot of wealth of knowledge to fiber optics and that we can now transport into the seafloor. The big innovation is putting power on the seafloor, and so we right now provide 8 to 10 kilowatts of power in these large nodes on the seafloor that gets distributed out to 400 watts in localized environments, and then down to 12 and 24, whatever you need. But in doing so, that conversion, it creates a ton of heat. And so one of the big engineering challenges is putting these large nodes on the seafloor that do these conversions underwater and dealing with the heat and engineering problems that go with that. So this is an example of we contracted with L3 Meripro. Turns out we're going to be laying the cable this summer. We have the shore station bought. We're leasing it right now, and it's being fitted out with all the equipment that goes in there. And then we have these primary nodes, which do the major conversion of the power, but they also help transport the data up and down the network. Each one of these nodes is about $2.5 million, and so we've tried to put these fiber optic cables, the backbone part, in safe areas away from. If you ask the telecommunication industry whether they would lay fiber over an active volcano, they probably wouldn't like that idea, even though they just didn't know it. So the other issue that we have is that because we're laying fiber on the seafloor in fishing areas, we've interacted with the fishermen a lot. On the West Coast, one of the reasons they're so successful is that there's a fisherman and cable committee, and they actually, when we went through the whole permitting process, they interact, and they have to we actually had to move our cable system so it didn't impact their fishing areas. And so we also bury the cable out to 1,500 meters water depth. So if there is a inadvertent dredging event where they're dragging along the bottom, they won't snag the cable. So we've done probably 3 years of permitting. We've done a full cable route survey with fishermen on board, so they could okay what we're doing. And that's been. And then we had about a 2.5 year permitting process. So right now we're ready to go. We've bought the fiber. It'll be installed this summer. The next summer, the primary nodes will be deployed. These things, so this is about 12 feet across. These are the ones that we're going to have are a little bit smaller than this, but there's a person that can stand just about there. One of the interesting things for operations and maintenance, so we don't have to recover these things, is they're wet mateable connectors. So a robotic vehicle can come in and connect fiber and disconnect it. And then at the experimental sites, such as an active underwater volcano or a methane hydrate deposit, we have much smaller nodes, and they distribute the power to the sensors in these key sites. So this summer we're going out for 3 weeks, and we're going to look at in detail and confirm all the experimental sites where the sensors are going to be, and then we'll deploy it in 2013, most of the sensors. And in 2014, we have full water column moorings that go from 3,000 meter water depth up to just about the surface, and I'll show you some images of that. With fiber right now, this isn't exactly, it's not the, you can transport terabytes of data on fiber currently, but ours will use initially 10 gigabit, it'll provide 10 gigabits per second of communication, and if we light up, each fiber has 24 wavelengths, we can get up to 240 gigabits per second and 8 kilowatts power, which we can also upgrade. So one of the nice things about this is this system is very, very expandable as new technology comes along. Things like in situ flow cytometers or in situ sensors that can measure DNA. It's a very expandable system, and we'll be able to accommodate new technologies as it comes along. It's a very diverse science area, some really incredible processes, very, very dynamic, and also processes that are very societally relevant. So I'll show you a slide a little bit about ocean acidification, but this area is undergoing really profound changes that weren't anticipated until about 2050. For those of you that do a lot of fishing or have been around the Gulf or off the coast here also, there's hypoxia events where ocean water that comes, we think, down from Alaska, although we don't know that. Deep ocean water comes up along the continental shelf up to the slope and creates these large die-off of animals that live on the seafloor. And we don't really know, they seem to be increasing over time, and we don't really know the reasons for that. So a lot of areas in terms of climate change, there's decadal changes that go on off the coast here. For me, these are some of the why we want to study the Pacific Ocean. So we have both El Nino and La Nina events that are relatively regular, that impact whether we're going to have a very dry winter or have a lot of snowpack. And those are influenced also by decadal changes. When those decadal changes get put on top of the more commonly occurring El Nino, La Nina events, they can really perturb the ocean and our weather significantly in the Pacific Northwest as other ways. And I already mentioned the low oxygen and the ocean acidification. And so we have these basin scale currents that come across from Japan here, the subarctic current and the western drift. And right up in this area, they bifurcate. And there's some really important biochemical processes that go on when these waters that come across the margin here turn off and go up to Alaska. This is Global Station Papa here, and then turn south along the coast here. And one of the reasons that this is so critical is it also brings upwelling of nutrients in this area. So major fish production in this environment. So there's some fundamental large currents that impact our planetary oceans, and one is the eastern boundary currents. And the eastern boundary currents, a lot of the anchovy industry is impacted depending on what happens along this margin here. So what we've tried to do is pick this area here where if we can start understanding in good detail, if we instrument one site well, and we look at the processes that go on in this one environment, that they may be good examples in starting to understand areas that are very, very similar, but which we do not have instrumented yet. It turns out that this site here in the Pioneer Array, right off your shores here, this is where there's a western boundary current. So these places were chosen as exemplar areas where we can put a lot of infrastructure in one place and start understanding planetary processes in more detail. And this just shows you a zoom in here. This is going to be a satellite image, but if you look at the effects of coastal upwelling along here, this is chlorophyll, so a measure of the productivity in this environment. And what you see is during certain periods of time, it's a seasonal, you see a very, very large impact in the chlorophyll or primary productivity in this area, which impacts the entire food chain in this environment. So it's a very dynamic system that we aren't often in the right place at the right time. The Pacific Decadal Oscillation is when there's a change in temperature. And you can see here in the negative phase here, you get these colder waters off of here in Alaska. And in the positive, in the positive phase and the negative phase, over here you get warmer waters. And so one of the interesting things is if you look at the fishing industry off of our coast, it directly correlates to this decadal oscillation event. And at certain times, this is for salmon, the entire Chinook return of salmon crashes depending on what phase we're in for the Pacific decadal oscillation. Turns out when the fish go offshore, we don't have a good tracking mechanism, so we don't actually know what, from year to year, what the fishing industry is going to be like for, you can pick salmon, but it's other fish as well. And it's a huge, if you look at the eastern boundary currents, they're 35% of the global marine catch, and it's $1 billion industry off our coast. So it really is societally important to understand what goes on there. And to be able to predict, if you know something like this is coming on, you might want to decrease your stock for your fishing for a year or so. You're certainly familiar with El Nino, La Nina events. In the Pacific Northwest, we certainly know if it's a La Nina, we get a ton of snow as more buildings are going up. During El Nino events, when we get these droughts, we have water rationing and things like that. So this is all driven again by what's going on in the oceans. And then this just shows you one of these hypoxia events. So this is dissolved oxygen here. And what you see, this is low oxygen, higher concentrations of oxygen. This is the shelf, it's exaggerated, the shelf off of the Washington, Oregon coast, and you see what happens is there's upwelling of very oxygen depleted waters. And this is Grace Harbor. These blue areas are where there's been dead zones, where there's huge amounts of die-off of many of the benthic animals in these environments. And again, they seem to be increasing over time, and we don't really know why that's occurring. And then ocean acidification, it's been in the news a lot. And the Pacific Northwest turns out to be, if there is a great place to study it, is that the signal to noise ratio is very high here, meaning that the amount of corrosive waters that we're seeing that were at depth are now appearing at much shallower levels than they were, and that these changes weren't predicted to occur until 2050. So there's some events that are going on, these nonlinear changes that our models are not able to accurately predict right now. So until we get the right amount of right kinds, the right time scales, the right spatial scales of data, we can't really make the right models that we need to. And so this will be over the next 2-3 decades, this is going to be a very iterative process where we provide the real-time data. We can change the sampling rate to the modelers. The modelers adjust their data over several parameters because we'll have the right kind of information. They change their models. We go collect more data, and we have this iterative process. And so the hope is that we can create these models that help us, and more complex models that really help us better understand and lead to better predictive capabilities in our oceans. So this is what the coastal off of Newport, Oregon here. It's about 130-kilometer extension of fiber optic cable that goes from 25-meter water depth. There's uncabled systems of moorings. This is a very, very dynamic surf environment. 80-meter mooring here that'll be connected to the fiber optic cable, and then another full one at about 500 meters, then another water column mooring at about 3,000 meters. These are a hybrid type of mooring. They're a brand new engineering design where there'll be a profiler that has sensors on it that makes several trips a day with from 3,000 meters up to 200 meters. Then there's a 200-meter platform with a lot of sensors, including cameras on them. And then a winch profiler that also has a bunch of sensors on it, and it'll go from 200 meters to just up to the sea surface interface several times a day. This is a lot of power, 3,500 watts. We can put a lot of different sensors. It's expandable. And so we're really looking forward to having this network across the entire continental shelf slope break down into deep water and starting to see if we can see this upwelling of low oxygen water and impact of ocean acidification. And they also have biogeochemical sensors, so we can start looking at, say, the zooplankton, see how they're impacted by these events. So I've gone through tried to give you a little bit of impression of the kinds of water column key science questions that we're looking at, and some of the problems that we're looking at, and the infrastructure associated with that. And so this is a kind of that example again of the complexity with the oceans. But my love is submarine volcanism. So I spent a lot of time in the oceans looking at how volcanoes impact the planet, and how volcanoes sustain life in the absence of sunlight on the planet. So off our coast, we're very lucky in some ways. So this is the Pacific Northwest here. This is a very large subduction zone. We're overdue for a 9 magnitude earthquake. This has been locked for several years now. But if you go about a day's steam off the coast is where the spreading center is. So where there's upwelling lava, the ponds beneath the seafloor, only a couple kilometers beneath the seafloor. And you have very, very hot melt, 1200 degrees C. These volcanoes look like Iceland or Hawaii, except that they're usually 2,000 meters down, 7,000 feet down. So a lot of people don't get to see them. And because there's a lot of heat down there and seawater migrates down into the crust, it creates these very large convection cells that form these 380, 400 degree black smoker systems, and I'll show you some imagery on that. So I spent the last 30 years or so studying this environment here, and I'll try and share with you why I think it's so cool and some of the excitement here. So some of the things that so we're going to have a large seismic array out here. We're going to be looking at, one of the things that we don't know is, so this is the spreading center. It's spreading about the same rate as your fingernails grow. There's a large transform fault here. It's like the San Andreas fault almost. It's where the plates are spreading apart. There's large earthquakes that go along there. This is where we hope to extend the cables at some point in time. Right now, our cable extends from here out to the Juan de Fuca Ridge to axial seamount. I'll show you some imagery of that. It's the most volcanically active volcano on the spreading center. And then we have another route that comes down through here to look at how methane is stored in the ocean crust and what happens to it when there's large earthquakes. And then to me, where I think some of the most exciting discoveries are going to be made is to look at how life thrives in these extreme environments of hydrothermal events. But again, these we just don't have any time series measurements at the right scale or the right temporal or spatial scale in these environments. So I think even my prediction is even within the first 6 months, we're going to have some really exciting data that will come ashore. So one thing we're very lucky with, if you look at plate tectonics, the major processes of how ocean crust forms, how the continents move around, these are little plate boundaries here where the spreading centers are, where 70% of the volcanism occurs on the planet is along these boundaries here, and I'll show you a slide of that. And then if you look at the Juan de Fuca plate, we're really lucky because it exemplifies much larger plates, but all the processes that go on in these larger systems that would be very hard to study at those scales happen to be on a quite manageable system off the coast of Washington and Oregon. So it was one of the reasons early on that John Delaney chose this area to instrument. So this is clearly seismicity has been in the news lately, and if you look at this is from 1970 to 2010. The yellows, oranges, the larger size of the balls, and the warmer colors are the larger magnitude earthquakes, and you'll notice that they form along these major plate boundaries. But also what you're going to see here in a second is that from about 2000 to 2010, you start seeing these very, very large earthquakes increasing over time. And we first thought maybe this was a problem with how the data are recorded, but my seismic friends say that this seems to be a real trend that over time we're seeing a lot more of these quite large earthquakes. And we don't actually have seismic arrays. There's only a few seismic arrays in the ocean seafloor. So this is something that was driven home. We made this slide recently, but it was driven home to us. So this was the Chilean earthquake. It was a 8.8, I believe. The Sumatra, and then more recently the Japan earthquake. And Cascada is where historically there have been magnitude 9 earthquakes. There's very, very strong evidence for that. And so one of the things that we've struggled with is how can we predict these type of earthquakes? How can we have a better understanding of why they occur? Are they really increasing over time? If there's a large earthquake over on the Juan de Fuca Ridge, does it impact the seismicity along the margins? We don't actually know that because we've never had instruments on the seafloor right now. The Japanese spent a large amount of money. They have one of the first cabled observatories, and they spent, after the Kobe earthquake, which created billions of dollars of damage, they put a large seismic array off the coast that provides an early warning detection system. Unfortunately, it was a little farther south than where the large earthquake just happened. So we're hoping that over time, we'll be able to do the same thing. This is the lock zone, again, where the plate is diving underneath the boundary right along here. It dives down, starts melting and forms the Cascade volcanoes, but it hasn't moved for over, the last major earthquake was about 1700. So it seems to have a repeat of 400, 500 years, and maybe less from looking at the newer data. So as a start towards that, a plate scale seismic array. This is our Canadian colleagues up to the north here. These are the locations of where we have seismometers and high pressure, very high resolution pressure sensors on the seafloor. And this is the start of the array down to the south. The pressure sensors that we have out there now are providing real-time data. They measured the tsunamis that came onshore from the Japanese event. And one of the critical things to realize is NOAA has a DART array of buoys, but they're pretty far offshore. And what happens during these large events is you may not have a good indication from the large moorings offshore of how big a tsunami event might be, how big the waves are, how much time you have before it comes ashore. So we're hoping that with some of these closer in arrays that we may get some early warning detection of indication of how large the tsunamis might be coming onshore. Some modelers that I've worked with suggest that if we have the seismic array in the right place, that we may gain anywhere from 10 seconds to 2 minutes warning, say in Seattle, depending on where the earthquake first hits. It turns out seismically the historical events have started in the south, and basically this entire subduction zone is unzipped from the south to the north. And Seattle, Portland, Vancouver, Victoria are all along this array. So it's really critical that we start having a good understanding if there are precursor events. Can we start modeling if we can really predict when these might happen? And if we can get an early warning detection system, you can imagine scenarios where we could turn off the power, for example, or turn off gas lines so that you don't have to worry about some of the big fires that Japan's had to deal with. The other thing that's of interest is, so there's gigatons of methane that are stored in the coastal margins here. And what happens is as the plates move, they collect a lot of sediment and they pile up right along the shore or along the margin. And as they pile up, kind of like you can imagine a snow plow that piles up the snow along the side of the road. Well, the subducting plates basically do the same thing. And so along the continental margins around the world, this is not unique to off our coast, there's large amounts of sediments that gets crammed up against the margin. They undergo a lot of compaction, they heat up, and a byproduct of that is there's a lot of microbial activity, and methane is expelled from the sea floor. But it's in this unique stability zone. It's kind of metastable, and so in some places, very, very common, this methane forms an ice compound called methane hydrate. And it's been estimated that there's gigatons of methane stored along the continental margins. And so there's a lot of interest right now as we start looking for new reservoirs for power generation or whatever, for energy. There's a lot of research going on right now into these gas hydrates and how they change over time. Because they're metastable, there's been large earthquake events. It releases these large amounts of methane perhaps into the water column, and methane's a greenhouse gas. So there's some predictives. Some people would suggest that this may impact climate over time. So again, there's a lot of societal relevance to look at methane stored along the continental margins. It also turns out that they also have some really cool microbes that live in these systems, so some really extreme environments. So one of our first studies that we picked to start looking at both the earthquake subduction zone processes, large seismic events, and smaller ones along the coast is we picked this area off of Newport, Oregon, in a place called Hydrate Ridge, which is right here, where there's a large methane deposit. That's one of the best studied places for methane deposits in the oceans. There's been some ocean drilling programs, like 2 ocean drilling program legs there. And it's this, you can see this kind of bump here, topographic bump here. This is 3,000 meters in about 40 kilometers or so. It goes up to about 700 meters. And this elevated section here is where the methane hydrate is. So we've zoomed in on that, and this is what it looks like when it's on the seafloor. This is from a site off of Vancouver, but this white material, some of it's bacterial, but some of it is this methane ice compound. It's, again, very, very common throughout the continental margins. This is a site, so we went out. One of the reasons, one of the difficulties is making sure that we have all the right sensors in the right place, and we have to measure cable lengths to meter resolution. So this is a map. It's if you look at the bathymetry here, this is a map of the main area that's actively venting, and that hummocky topography with large pits is where methane, the hydrate, has broken apart, dissolved, and it forms these large pits in the seafloor. It's not much topographic elevation here. This is from 785 to about 700 meters beneath the surface. And what I want to show you, the seawater surface, I'll do a transect along here to give you a sense of what this environment looks like. So this is some imagery we took last year using a robotic vehicle. We had 20 students out with us, so they got to participate in this event. These are bacterial mats. There's a lot of methane coming out of the seafloor here, and these organisms thrive in this environment. There's also things like clams that have special organisms, chemosynthetic organisms in their guts. It's a very hummocky, it's a little bit light in here to see, but it's a very hummocky environment. These are large filaments, filamentous bacteria. We'll zoom in here in just a second here. There's a lot of shell debris. These are the clam shells. There's crabs that come in here and munch out on some of the clams here. So a lot of chaff, and these are every place there's filamentous bacteria is where there's active methane coming out of the seafloor. And you can see, we're going to take a sample here, but you can see the filaments when we dig into this a little bit more. It's a very unconsolidated material, and you'll see in a sec there's a lot of flow that comes out of this. One of the problems, though, is because we haven't had sensors, we don't actually know the flux of methane out of the seafloor in many of these systems. And when there's a seismic event, say there's even magnitude 3 or less, what does that do to the flow of methane out of the seafloor, and how does that impact the microbial communities and the larger animals that live in these environments? And here you can see there's a pretty large amount of flow in this system, and then these are filamentous bacteria that live in this system here. So in order to look at this environment in detail, this is these nodes that I talked about that provide, basically, they're like extensions in your wall to plug in a light. They provide, each one of these little boxes here is a place where you can plug in a sensor. We'll have these seismometer arrays to look at the seismic events, very small events to large events. These things have plumes of bubbles that reach up several hundred meters into the water column that carry the methane with them. So we'll have upward-looking instruments to do that. Things to look at the tides. The lunar tides actually affect fluid flow in the ocean crust, so there's a tidal variation. You can look at the bubbles coming out of these environments, and they change over the tidal period. Chemical sensors. This is a great, we're now being able to put mass spectrometers, things that normally people would have in their lab that used to be, I can remember the early ones were very, very large. Now they're about this large. And because we have power, we can put them on the seafloor. Things to take fluid samples, and then we'll have cameras in this environment. So when this thing comes online, you could be sitting in this audience in your house, in the classroom, and looking at live imagery of the methane and the biological communities in this system. So something that we've always wanted to do and never been able to. So I'll spend a few more minutes talking about volcanoes. It's definitely something that my early career was looking at cascade volcanoes, and then I moved into the ocean. And I mentioned this before, is that about 70% of the volcanism on the planet occurs underwater, and yet we know very little about it. We've never been, only about 3 cases where we've been to an eruption as it was actually happening. And this is an area of interest for me, in particular, of how these volcanoes support life in the absence of sunlight. So here's an environment where it's 2,000 meters deep, can be a lot deeper than that. And these microbes have learned how to use the volcanic gases that come out of the volcanoes to thrive and evolve over time. And I think this is where there's going to be some really interesting discoveries, and I'll show you some examples of that. So again, this is just the Mid-Ocean Ridge Spreading Center. This red here is where the active volcanoes are. They're probably erupting all the time in different places, but there's only a few places in the world where we studied or been there at the right place at the right time. And so one of the interesting things, if you look at the volcanoes on the continents, and then you look at those underwater, this is a diagram that shows the volcanoes. This is just their radius, so how big they are from 100 kilometers across diameter to about 3 kilometers here. So the blue ones are smaller volcanoes, and here's Hawaii off here. The white ones are larger. But what you see in the Pacific is there's a huge number of volcanoes. Some of them are active, like Hawaii, obviously. Loihi is a new one that will soon someday reach the surface. And then a lot of these are what most people used to think was they were extinct. But it turns out that although they aren't volcanically active, that the ocean crust has a memory and sets up its own hydrothermal circulation cells, such that some of these volcanoes act as downwelling conduits. So seawater migrates down into the conduit, into the volcanoes. It can migrate perhaps 100 kilometers away from the volcano, increase its heat, change its chemical properties, have unique biological communities that thrive in there, and then it exits other volcanoes. And this is a relatively recent discovery. So as I mentioned, so some of the reasons that they're important, again, huge amount. This is one of the first volcanoes ever witnessed on the seafloor erupting. You can see this. One of the nice things about having pressure is that you can actually be near the volcano when they're erupting underwater. You'll see some lava coming out on the seafloor. And this is a volcano called Mata. Mid-ocean ridges it's the way our ocean crust forms. So most of the planet is formed by this process. There's hundreds of thousands of volcanoes, active and inactive, on the seafloor. Only 2 or 3 have been witnessed. They're a very important source of metals. So a lot of the ancient metal deposits that the Romans say mined came actually from seafloor environments. And they're still an active source of metals. So if you go into Japan, a lot of the hydrothermal systems are boiling, which is what basically forms metal deposits. In this case, it's underwater. So the Japanese and other countries, Papua New Guinea, are starting to mine these volcanoes on the seafloor for metals as we deplete our metals on land. But they're also shallow. When they're shallow, they can be very unpredictable. And so the best example is that of Iceland, right, where it's breached the sea surface now, and it had a pretty dramatic impact on plane schedules, and actually cost a lot of money. So we don't actually know how often they erupt yet. We don't know the size of the lava flows, and they're all associated, again, most of them, with these spreading centers. And so one of the key things that we're looking at with the Cable Observatory, by choosing this one very active volcano, is to look at the interactions between volcanoes, earthquakes, and life within the seafloor and on the seafloor. So this is just a cross-section of an oceanic volcano. This is what it would look like in Hawaii. It's almost identical on the seafloor, just that you're over a mile down. The oceanic crust, where these plates are spreading apart, usually between 1 kilometer, maybe 2 kilometers if you're in the Pacific, maybe 5 kilometers if you're in the Atlantic. There's a molten pool of 1,200-degree lava beneath the seafloor. And so what happens is, as the oceanic crust cools, seawater migrates down through here and sets up these very, very large convection cells, which drive the hydrothermal systems. One of the main reasons is that volcanoes erupt on the seafloor is they have a lot of carbon dioxide. So as kids, or even by accident, you take a pop bottle and shake it up, take the lid off, you know what happens. Well, the same thing happens in underwater volcanoes, where these melts have a lot of CO2, carbon dioxide. The oceanic crust will crack, and there's a very large explosion actually, that forms plumes that rise up several hundred meters into the water column of warm water, kind of like a Mount St. Helens type plume, except in this case it's warm seawater. So some of the reasons that I'm particularly fascinated with these environments, this is a place in 1993. There was an eruption on the Wanafuka Ridge. And what you're looking at is a crack on the seafloor about this large, where there was no hydrothermal venting, no seeping of fluids before. And all this white material is produced by microorganisms that live within the seafloor. And this was, in the early 90s, there was starting to be hints that there was a deep biosphere that lived in the seafloor to some temperature. We don't know the upper temperature limit of life yet, and we don't know lots about these microbes, what they do. But there's a hypothesis that if you took all the biomass on the planet, all the living material on the continents, and you compared that to the amount of biomass in the seafloor, the biomass in the seafloor rivals that on the continents, but we know almost nothing about it. So John Barros' students sampled these fluids, and what they found was when they looked at the microbes living in the fluids, that even though the surrounding background of seawater is 2 degrees, the fluids they sampled was about 30 degrees coming out of the seafloor, and the microbes required temperatures of 90 degrees C to live, and they also required that there was no oxygen. So that really drove home that to some depth beneath the seafloor, there's this subseafloor biosphere of very, very unique organisms that thrive in the absence of sunlight. They live off of volcanic gases, things like carbon dioxide, hydrogen sulfide, methane, hydrogen, and they live at very, very high temperatures. So one of the rocks we recovered in 1999, we turned over to a microbiologist from a hydrothermal vent site, and the highest temperature organism on the planet was recovered from that rock. It grows at 121 degrees C, and we're actively doing experiments now that in situ on the seafloor that suggest to us that the temperature might be quite higher than this. So it's a very exciting area of interest. Let me see if I can go backwards here and show you this black smoker here. So this is a black smoker called Sully that we've studied for about a decade here. The fluids come out at about 350 degrees, 400 degrees C, so about 700 degrees Fahrenheit. As they migrate through the crust, they become very acidic. They leach the metals out of the rocks, and they start up these large convection cells. And so by the time they enter the seafloor, which is 2 degrees C, seawater about, the metals all precipitate out from the hydrothermal fluids, and it forms these black plumes. But those plumes are basically fool's gold, pyrite, chalcopyrite, a lot of different sulfide minerals. So we know that after many of these volcanic eruptions that there's been a microbial bloom of microorganisms. In some places we call them snowblowers, where if you go down with a vehicle on the seafloor, you can't even see the seafloor because there's so much of this biological material coming out of it. So we think because the volcanoes have CO2 that during and after an eruption there's a lot of carbon dioxide coming out of the volcanoes, and it induces these large subsurface plumes of microbes. There's also reasons, so they live in very toxic environments, hydrogen sulfide, anything that would kill us. They love arsenic, they like mercury, they can process mercury, they get their energy from mercury. They can precipitate out uranium oxide, so people have put them in test tubes with dissolved uranium, and they actually precipitate uranium oxide, so people are looking at it for bioremediation purposes. The mining industries have known this for a long time. It might rival that on the continents, but it also may be that a lot of people are looking at the new pharmaceuticals that they'll come from the sea. And so the idea is that if you take these microbes up and recover them from the seafloor, you stress them out, that some of these microbes, when you stress them out, produce different kind of antibodies. And so the medical industry or the pharmaceuticals are interested in these environments to look at new medicines from the sea as we start being more resistant to things like tetracycline and penicillin. So there are some good reasons to look at this environment for societal reasons as well as exciting scientific. So we've chosen this volcano. This is the spreading center again. It's right here. It goes from about 3,000 meters water depth. This is the fiber that will come from the shore. There's a large node here where there's going to be a full water column mooring. And then it goes about 40 kilometers up the side of this volcano. If you've seen pictures of Mount St. Helens, this is a equivalent in some sense. This is a large caldera. This is underlain by quite a large magma chamber. It's volcanically active. It erupted in 1998. And one of the fascinating things to us is the sea floor here is inflating at 15 centimeters a year, which doesn't seem like a lot if you're on continents, but if you study tectonics and geology, something where the land is uplifting at 15 centimeters a year, that's a big event. And what it tells us, what we think it tells us anyway, is that there's melt being accumulated beneath this volcano and the gases are accumulating, and so the sides and the sea floor along the caldera here is inflating. And the prediction is, looking at that trajectory, that maybe in 10 years or so, maybe less, it will erupt. So we have a fiber that comes up to the edge of this caldera here. We didn't want to put it where the last eruptions were. And then this is a very active site of hydrothermal flow. And then these are geophysical experiments here to look at the volcano and how it's going to behave. If you were around for Mount St. Helens, one of the key signatures of a volcanic eruption or an imminent volcanic eruption is there's thousands of earthquakes every single day. They're small. They're called harmonic tremor. And so we put these seismic arrays out here to look at that event when it starts happening, and presumably we'll be able to see an increase in CO2 and predict that a volcanic eruption is imminent. So I mentioned this before. This just shows the downflow zones where cold seawater migrates down. In this case, in the volcano, it migrates about 1.5 kilometers beneath the seafloor, gets near this very hot magma chamber and rises, and then produces fluids that are in axial seamount or boiling. So we've these are the sensor arrays that are actually funded by the National Science Foundation that will be installed as part of the permanent infrastructure. And we're paying the whole operations and maintenance cost is also covered by the Science Foundation. So you'll see seismometer arrays, things to measure temperature, current. We're going to have a dedicated high definition camera, so it'll bring HD imagery directly into this room, on the internet, wherever you want to look at it. Mass spectrometers, it's one of the only sites in the world where we've been able to look at the evolution of microbes over time after a volcanic eruption. There's some interesting stories to go with that. Pressure sensors and tilt meters to look at the inflation events, and then a lot of chemical sensors. So all these will be interactive. So the idea is when there's an event happening, we can change the recording time, what the look angle of the camera is, and start trying to see if there's a underwater earthquake here, magmatic event, what processes change in these environments. One of the things that we did is we take this. I forgot that there was sound on here. I don't know if it's connected. But we took a bunch of students out with us, and they're everywhere from freshmen to graduate students, from oceanography majors. Oh, good it is. And we took two students from digital arts that came out, and so they took a time series of, in 4 or 5 days, what it's like to load the Thompson, the ship that we normally use. So the ship's about 270 feet long, and this is putting all of our. They're completely empty. If you've looked at the URI boats, they're the same. They're completely empty pretty much when you get on board. And within a few days, you cram a lot of stuff. So in this case, we had a robotic vehicle and an autonomous vehicle from Woods Hole. Gives you a good sense. So this is a robotic vehicle called Jason that we used. It's connected to the ship by a fiber optic cable. If only it went that fast. This was a sunny day in Seattle, so the labs are all empty. We bring all of our science gear. Hopefully you don't forget anything because you don't come back in. So we go through a set of locks to get out into the salt water out in the Puget Sound. So great. So yeah. It's one of the, I think one of the, I wouldn't say unexpected pleasures, but it's one of the reasons I really love taking students to sea, because they see things differently than the way I do now, and they're just always enthusiastic and a pleasure to be around. So this is some of the imagery from axial volcano. This is the 1998 lava flow shown here. And this is a pretty long-lived hydrothermal field right along this. This is a big fault that runs around this caldera, which is basically where there was when there used to be a large magma chamber there, the melt drained out, probably along the flank somewhere, and the whole valley floor subsided by about 100 meters. And so it's left with this big depression, and then there's these hydrothermal vents. There's 3 hydrothermal vents. These are these black smoker chimneys. There's quite a number of them. And then unique macrofaunal communities. So these are tube worms that live in this environment. We're going to zoom here in on the Ashes field just to give you a sense of what this looks like. So last year, because we had to know what the geometry of the vents were, how close they were, where specifically within a meter or less, where we're going to put the sensors, we took an autonomous vehicle, and we also took Jason out there, and we mapped this in sub-meter resolution. So what you're looking right here is about a 4-meter tall chimney called Inferno. We didn't name these. NOAA had a observatory out here for quite a long time. Gone out there almost every year. So we're going to zoom in on what Inferno looks like here. We've photomosaicked these chimneys. I have an undergrad student that works in my lab where we take multiple images, and so you can't see this out of the sub window, the whole structure, but this is what it looks like here. So that's that one chimney we're looking at, and this is the kind of imagery that we're going to be streaming in live in real time. These are beautiful animals. These are limpets, palmworms, very, very diverse animals and very dense animals. So all that hairy-looking material are all tube worms. You can't even see the sulfide, the metal sulfides in most places because of the animals that grow on these, that colonize the structures. The youngest portions of the chimney right here, the hottest temperatures, are higher in most cases than what the animals can live on. But again, this will be streaming live when we get the system in place here. So the idea is, it's one of the reasons I wanted to come out here to talk with people, is that you can imagine a scenario where you have museums, classrooms, and there's event walls. And you could pick the event that you want to look at. In this case, what you're looking at is real earthquakes that have taken place, recorded earthquakes over a year period along the Juan de Fuca Ridge here. And so you could look at hurricane tracks, hypoxia events, black smokers, and the idea is you could zoom in. So say that you look at this event and you see that there's something happening, there's an earthquake occurring out on the Juan de Fuca Ridge, and you zoom in because we'll have the imagery to do so, and you see that there's seismic events going from the top of this volcano along the flank, and that's a characteristic signature that there's an eruption going on. And so you want to look in real time now, and you want to zoom in on this and see what's going on. And this is where the fiber will be. So this is one of the moorings that we're going to have in place. This is a 200-meter platform. This is the sensor array that has a profiler that goes up and down. And so we'll be able to visualize in a 3D environment. This is the actual bathymetry of the caldera floor here. These are the hydrothermal vents. And so you could pick the instrument that you wanted to look at. So we're looking down at the bottom of the sea floor here. These are the instruments. We have accurate models now. These are looking up at the water column. We're going to drive along the seafloor. Our eventual goal is to have autonomous vehicles that will be permanently docked there that can fly back and forth along the seafloor and map out the changing bathymetry, how the volcano changes over time, as well as the organisms. They can take images. And so what we've seen now, as an example, is that there's a seismic event going on. So what we want to do is we want to look at a seismometer, and then we also want to look at a camera and look at how the vents are behaving during this seismic event. So we go on to the internet and we zoom in and we look at the seismic record. This is this is a seafloor event about 30 kilometers away, but it's a good example. And you can look at that seismic event in real time and then pick your camera, and we'll be able to change the camera angle. And so you could imagine scenarios. We know these chimneys fall over during some earthquake events, or we believe that's true. The fluid properties, some vents now have completely shut down after a seismic event about 30 kilometers away from here. So they're very, very dynamic. And so we'll be able to look at this in real time and look at the various sensors. But again, students will be in the classroom. So this is an example where they're sitting in the classroom. They're looking at the same thing that we are in real time. When we're putting in sensors, this will be streaming live. This is a instrument that actually looks at the boiling processes, the fluid chemistry, and they'll be able to witness as we put in sensors, pull them out, And these are some tube worms here. But I think the take-home message is, as technology moves along, we all have these things we carry around with our pockets, unfortunately. And so we'll be able to look at not only these kinds of processes, but many, many other ones that are occurring in the world's oceans. So life in extreme environments, for example. As technology moves along, there's in situ DNA sensors that are being developed that actually go on the sea floor, that can be deployed in the vents, taking fluids out of the vents, that'll be able to look at the microbes in real time, tell you who they are and what they're doing and how many of them eventually, probably in the next 10 years or so. So seismic events, ecogenomics, not only in the seafloor but also the water column, these will all be interfaced with better developed ocean models. So you can imagine almost any instrument that you use in the lab now will be able eventually to put in the seafloor. We can deal with pressure. Everything's made out of titanium. All the electronics are put in titanium housings. So this is a looking towards the future, right? We're very excited, and the hope is that the students become engaged and they start using their intuition and excitement and build things that we wouldn't think of because we have certain blinders on. So this is a little bit old now, but this is 2008, and this is all these lines here. I don't know if you can see them in the back here, but all these lines are the cables right now, and they just finished a major install off of Africa, and one of the main drivers was because of the World Cup there. But the hope is connecting Africa now and a lot of the hospitals to the internet. This just gives you an example. I couldn't get these stupid numbers to change, but this is the year 1956. TAT1 was installed. The entire bandwidth was 2.3 megabits per second. In 2001, TGN Pacific was installed. It's 8 terabytes per second, and now they're up to, this is a way low number, so probably petabytes in the next few years, that are coming off of these little tiny, these are smaller than a hair fiber right now. And this is a jacket that shows armoring jacket. So the point is that, what we, just like your computers right now, the submarine fiber optic cable industry is getting more data for smaller fibers as we go along, and we'll certainly be able to put more power on the seafloor. So I think one of the exciting things is, although John Delaney was one of the first visionaries to start this, he's been thinking about it for 10 years or so. In the last 2 plus years, there's been 11 countries that have come to us and are also installing fiber optic cables on the seafloor for everything from seismic early warning detection systems. Taiwan's put one in, Japan's put one in, but also to look at China's building a fiber optic cable system. So what you see here is the green ones are ones that are either being installed for us here, right here. This is Hawaii, the low station. There's a proposal in to put a fiber all the way around a barrow through the straits here up to northern Alaska. The red ones are ones that are being planned in Norway. The Europeans will have a system called ESONet, which is supposed to drape Europe with these fiber optic cables. And so I think one of the things to think about is, as we become more and more of a global community and really depend, I don't think we can act independently much anymore to some extent, that these cable systems will let children of all ages look at these. We want to develop smart games rather than Mortal Kombat and video games like that, where you can develop science games with real-time data coming in, and they're interactive. So you can imagine kids in China or Africa interacting with students in the U.S. at all ages and learning how to look at these systems over time and why they're societally important. And so what we're lucky in right now is that we really are at an intersection where a lot of the technologies that are not driven by oceanography at all, we're now being able to take advantage of. So if you look at nanotechnology, this is a fiber that when you wear, the friction creates heat, warm you up. Certainly cloud computing, grid computing, Microsoft, Amazon, things like that. Optical fiber, power, different kinds of fiber. Robotics, the medical industry has been way advanced in robotics, and we can use some of that technology to be better adapted to, say, when you want to grab onto something with manipulators on the seafloor. We can use some of their technology to have more dexterity. Certainly ecogenomics. And then one of the really fascinating things is there was a Nobel Prize in digital imaging. So HD imagery is already out of date. They're going to be bringing on these 4K systems that have better resolution than what you can see at. So they're almost like putting microscopes on the seafloor. And so one of the, I think the really interesting things will be over the next decade or two is recognizing that all these technologies are changing very rapidly in very nonlinear ways, that because we have power and bandwidth on the seafloor, we'll be able to make use of these things. So I'm just going to end with this because I think it's one of the most, for me, it's a really beautiful image, and it's the kind of thing I think we can bring to people. This is a 7,000 foot, this is an old black smoker, extinct chimney. It's about 7,000 meters water, 7,000 feet beneath the sea floor. And this is an octopus that we found in 2005. And we were streaming imagery from the sea floor up to a satellite and onto the internet on shore. But we fondly call these things Dumbos. They have a more formal name that you don't even know, but I think they're one of the most graceful, amazing animals. John Barros, a colleague of mine who's a biologist, works on a lot of vent animals, and he says that their eyes are very closely related to human eyes, which I find fascinating since there's no sunlight down there. It's a very graceful, we don't know how long they live down there. They're very intelligent animals, we know that. But yeah, I'll just leave you with this imagery because I think it's not something that you would predict to see, but it's graceful and I like it. So I want to thank you for inviting me, and if there's any questions.
We just wanted to note that microphones will be passed around on the sides. If anyone has any questions, just raise your hand.
I was wondering if you guys have a plan for managing
Yeah, great question. So one of the challenges is in particularly where there's sunlight that filters down through the ocean surface water. It's a very productive area, and lots of organisms love to grow there. There's lots of nutrients during certain times, and so a lot of some of the key sensors that we're putting down, when you leave them for a year, their membranes get covered with animals, or the cameras will get covered with animals. And so there's a couple things that are happening. One is because we have power, people have thought of putting like brushes that will, windshield wipers on the cameras that'll come back and forth. We've looked at using ultrasonic cleaners. We've had some use with that. But also because of other reasons, people have developed these, the newest one I saw was built by, it's a company in Europe that normally builds a lot of infrastructure for oil industries, which has some of the same problems we do. And it's a completely clear membrane that you could put it on an optic system and it wouldn't hurt it at all. And it seems to do quite a good. They showed us some examples where they'd covered a autonomous vehicle or glider, and they had one part that didn't have this membrane on it and one did, and it was night and day for the animals that colonized it. So I think there's some new developments. Without a doubt, we're going to have some issues, but I think new technologies will come along. And my view is, in so many of these environments, we have so little data and just single point measurements that if we got 6 months, in some cases, of continuous measurements before the sensor got degraded, in concert with all the other sensors around it, that we're going to learn so much that I think, in some cases, so the moorings, for example, the global moorings, in some of the areas, they're going to be going out every 6 months and recovering them. And one of the main drivers for us to put that platform below 200 meters or at 200 meters was so we might delay the biofouling on there. Our sensors were going to go out every year and recover. So good question, though. Yeah, it's a tough environment. So.
I was wondering how you're gonna present the information to the public via like live feed, if it's gonna be a website or if it's gonna be a program.
Right. So there's another component. So there's we're called the implementing organizations, the people that are putting the the gear in the water. And so it's, as I mentioned, it's a UW for the Cable Observatory, Woods Hole, Oregon State, and Scripps for the large moorings. And they just brought on a group for the education. They call it Education Public Engagement, which is led by Rutgers. So I think the MRESC pot of money is for infrastructure, right? So it's this interesting thing about education public engagement. And so it's supposed to be used for equipment, a large part of it. But because it's so critical, that part of it is how we reach the public. They do have a couple, 3 programs that they're going to put out that will be looking at how we present things to the public and how it's accessible. So for us, for the HD imagery, we'll actually be storing it in a little bit compressed because it ends up to be petabytes of data very quickly. But what we've done this year, and we'll do this summer, is we'll stream it live over the internet, and we put it at a resolution that it's not quite HD quality, but it's accessible on the web. And then as it's streaming live, we have students and scientists that type in like a CNN type statement about what you're seeing over time. So that's the model of what we think will happen when it gets turned on. We doubt early on that we'll stream the HD imagery live continuously from the hydrothermal vents. We don't know how light impacts animals, so one of the things that we're going to do is during some amount of period, we'll stream it live we're going to use LED lights, look at the biological communities over a day or 2, see if there's any change in behavior. More likely we'll stream the HD imagery probably 20 minutes in an hour, and then if we see events happening, we'll turn up the data rate. So it will be available. If you have the right system, you can get the higher quality. Otherwise, we downgrade it so it's more accessible for more people. It doesn't jam up your system. So. And I should say the other thing that's happening is you can imagine people are developing without humans in the loop ways to look at the high definition imagery, and so it'll be searchable. So it actually is smart enough that it will do animal recognition. So you can look at it and say, okay, I want to see in the last 24 hours when a crab came into view, and it'll search. It's smart enough that it'll bring up those data, and then you can say, okay, this part of the video is when I want to see what the crabs are doing. So the computing people are really interested, the internet people are really interested in this. So there's a lot of, for instance, Microsoft is interested in creating workflows where we can take a piece of information, do all the processing, and get it out on the internet so people can access it. And one of the things I think we need help with is how we develop these. I don't think we're very good yet because we haven't done it, of how we bring live data feeds into the classrooms and use that in an educational system. I know I would have rather had that than make an XY plot out of a book, but maybe that's just me. So. Okay, well, thanks so much.